Thank you very much for your time, Dave. I'd like to introduce you to my colleagues at the MIAPPA Energy Conservation Committee. This is item number 3C on our agenda. I think either Rich Robin or Steve Hawkwart will be presenting this, but Dave has an idea for a simplified wet bulb calculation for start control. As you can see, we are using the old MIAPPA Standards Council website for our agenda. Our attendees will have this. Not only will they have this link, but they'll also have this as a PDF that retains all the links to all the other issues here. So this particular presentation is specifically for Dave's idea that we'll be presenting to the ASHRAE committee. It's called a continuous maintenance proposal form. We've done a number of these, and we can likely send this out to the ASHRAE 13 or the ASHRAE 189 or the ASHRAE 90.1. So here's probably one area where we'll be probably presenting this idea to the ASHRAE committee, and then of course we have everyone's familiar with ASHRAE 90.1, and they're also familiar with 189.1. So this concept that Dave will be talking more specifically about will be presented to these committees as a new idea. So without taking any more time, I'm going to turn this over to Dave Anderson, and he'll tell us all about his thinking here. Go ahead, Dave.
Hello, everybody. This is David Anderson, and hopefully you can see my screen here, and it's large enough for you to read. First of all, a disclaimer. It's up to you to determine the suitability of these formulas that I'm going to show you today. They work in the cases that we use them for, but there are certain cases you might want to generate a wet bulb calculation for where this wouldn't be the calculation you would use. So just wanted to get that out there. In the 2013 ASHRAE Fundamentals book, you can see a section on calculating the wet bulb temperature, and given the dry bulb temperature, the relative humidity, and the pressure. We have dry bulb temperature and relative humidity that we read, as I'm sure most of you have the same thing, and you probably already have calculations for either enthalpy or wet bulb that you use for determining when to go into a free cooling mode. What we were looking for was a little bit more accurate formula, because the ones that we had been given by the controls manufacturer were based on kind of a table scenario, and so they didn't approximate certain portions of the curve the way we would like them, accurately enough. So sometimes it could be off by a degree or so, wet bulb, and if we're trying to determine whether it's okay to switch into free cooling mode, there can be a lot of hours involved where we wouldn't be able to use free cooling if we didn't have an accurate reading. So looking at the ASHRAE book for some guidance, there really isn't an equation that suits that we could use. Mostly they require trial and error or a numerical solution method where you use this iteration where you go through several cycles until you get enough accuracy. We didn't want to try to duplicate that in our control programming language if we could do something a little more simplified. So I took a little bit of time and went through some calculation adjustments and came up with a formula, and then with the help of Bill Verge, he helped me reduce the formula a little to get it a little bit shorter, and then we put this into use and we've tested it and found that it works very well for us. So I thought we would share this and get it out there as one of the practices you can use. Let me call up metric chart. So this calculation, what we're mostly interested in is the range where we want to decide two different things we use it for. One is when we want to go in or out of free cooling. Pretty much going out of free cooling, we just use the chilled water temperature. We can tell when it's getting to the point where we can no longer generate an adequate chilled water supply temperature, so we use that to switch out of free cooling mode. But to switch into free cooling mode where our chilled water temperature is fine, we use wet bulb temperature. So we're interested in that region where our wet bulb temperature would give us the desired chilled water temperature when we look at what the approach of the towers may be. So if I put a couple of yellow dots on here, if it was 50 degrees outside and 40% relative humidity, you've got a 40-degree wet bulb with a 3-degree tower approach, say, or even 5-degree tower approach. You could get free cooling at 43 to 45 degrees Fahrenheit. So we're looking at this region as wanting to make sure anywhere in here we're getting very accurate wet bulb readings. The other thing we use it for is determining whether or not the return air stream is has more or less enthalpy than the outside air stream. So in that case, we want to, of course, use the in the cooling season, we want to use the source with the lowest enthalpy. We tend, rather than using just the enthalpy numbers, which are less easy to understand for somebody out in the field, we want to use something more like the wet bulb temperature, since those are parallel lines here on the psych chart. So it's a lot easier to say, oh, my return wet bulb is 60 and my outside wet bulb is 58, so I'm going to bring in outside air right now, even though the chiller is running. So those are the two main areas where we want to make sure that our wet bulb calculations are accurate. And so that gets us all the way up into the, if it's 75-degree return air and whatever percent humidity, say 60%. Obviously, we want to make sure that that's being calculated properly. So given those constraints, just to let you know, if you're trying to operate and use this as a wet bulb calculation way down in the minus 10-degree range and so forth, it's not going to give you such an accurate result. It wasn't the intent of the formula. And likewise, when you're up in the 90s, you're not going to get the same or as an accurate result either. And that's, of course, you're going to be on that point anyway. So let me go to the calculation here. So here's the calculation, and since this is being recorded, you'll be able to pause it and write this down if you decide you want to give it a try or use it. So we're not necessarily sticking with the nomenclature that ASHRAE uses in the guide, but we use OAW for outside air wet bulb, OAE for enthalpy, OAD for dew point. Those are just our shorthands that we use in our programming. So this is the calculation for wet bulb. Enthalpy, we just take that same calculation, but we adjust it so we can get an enthalpy number, just in case we want to use that. Again, like I said, we usually use wet bulb, and we also use this formula for the return air temperature and humidity to calculate its wet bulb temperature and compare the two when we make our economizer decisions. And then the dew point, we also did a formula for that as well, so you can use this to read any of the three. I also provided in here, if you happen to have a Siemens system, here was the PPCL code that was used to determine that. So just to note, this B49004, that's our relative humidity, the raw point name, system name for that. This should be the exact same thing really as what you see up here. It's just we use OAT and RH for relative humidity. So anyway, that's pretty much it for the wet bulb and other calculations. We find this is a lot easier to implement in the code. It's a lot shorter. and it's worked well for us. So hopefully this will help you if you have any issues with your accuracy. Feel free to test it out, put it in there, and check it side by side with what you already have, and see how accurate yours may or may not be. Or you may find that if you have one that's more accurate than the one that what we have here, please share it, because I would love to see what that is. And I guess that's it, and I'll go. Hi.
Thanks very much, Dave. So do I understand that this is what controls the leading and falling edge of whether you're turning on a piece of air handling equipment?
We use it for turning on the free cooling mode, so we turning off the chillers and going into free cooling mode. One of the things we have to make sure is that if this wasn't reading accurately and we switch into free cooling mode and you can't provide the chilled water expected, then the chilled water temperature itself would be high enough to want the chiller to come back on, and we obviously want to avoid cycling the chiller on and off.
Mm-hmm. Okay, so ultimately the idea here is to use energy more effectively, and for that purpose this is exactly what we need more of. I've only heard good things about this from other people, and my hope here is that manufacturers will be watching this, will take note of it, and that the other confirming performance of this might be undertaken by some of our colleagues at the MIAPPA conference. So, well, all right, Dave, is there anything else? I would invite you to do some follow-up. We could possibly think about seeing if we get any data or any confirming or denying information from the ASHRAE committees, but you and I will prepare a continuous maintenance proposal for the ASHRAE committee, and we'll see where that goes. So if there's any data that if others like to be involved in this, of course, you're welcome to join the discussion. I'll put this in on the agenda of our February 17th meeting of the mechanical engineers. One thing that I was amusing myself with was when I saw your psychometric chart there, I was reminded why I preferred electrical engineering over mechanical engineering. Electrical engineering, we can do things with finite math, and we don't need to use all those charts and surfaces that you guys have. We're more comfortable with a Laplace transform, where we can simply come up with derive a single or double point solution. So I admire your insight and expertise here, Dave. And with that, I will close the call, and we'll see what kind of response we get from our colleagues at MIAPPA.
All right. Well, thank you very much for your attention.